Lewis dot drawings are very difficult to explain in writing because in order to explain a drawing, you need to be able to draw. I have constructed this video so that we can work through Lewis dot drawings and then talk about why we even care about such drawings. I know that I'm taking a significant amount of time building up the chemistry for you, but in the next module we head into the kitchen. We put all of this learning into practice. The Lewis dot structure is a pictorial representation of the atom that clearly shows the number of valence electrons. It also clearly shows how many electrons would be needed for the atom to reach the stable configuration that we call the noble gas configuration. And the noble gas configuration is when there are 8 valence electrons, and this is the octet rule that you read about. I have a very systematic way that I draw dots. It is as if there is a box that is surrounding the 4 sides of the oxygen, and the dots are added to these 4 sides representing the electrons. Oxygen has 6 valence electrons. So therefore, dot 1 would go here, dot 2 I place here, dot 3 I place here, dot 4 I place here. So I've gone around all 4 sides, and then dot 5 I would place here, and dot 6 I would place here. So this would be the Lewis dot drawing of oxygen. Since there are 4 sides to a box, and if 8 electrons are needed, then every electron should be paired if we are at that stable noble gas configuration. Electron configurations are always more stable when every electron is paired with another. It is obvious from this drawing that we need 2 more electrons to have every electron paired and to reach a total number of 8 valence electrons in accordance with the octet rule. These 2 sets of electrons that are paired are known as lone pairs. So they're called lone pairs. And that's a new term that I haven't yet presented to you in any of your writing. Okay, so we have figured out oxygen. Let's go ahead and move to another atom. Let's consider chlorine. Chlorine has the atomic number of 17, therefore it has 17 protons and 17 electrons. So let's go ahead and write out the electronic configuration. There would be 2 electrons that would go into the first shell. Then there are going to be 8 electrons that go into the second shell. And so then that is a total of 10 electrons, leaving 7 electrons to go into the third shell. And so what we've just determined mathematically is that there are 7 valence electrons. And so now let's go ahead and construct the Lewis dot structure for chlorine. Electron 1, electron 2, electron 3, electron 4, electron 5, electron 6, and electron 7. Okay. So that would be the Lewis dot structure for chlorine. So now let's talk about the other things we have learned. So first, how many lone pairs? Okay, all of you should have an answer now, and if you answered 3, you are correct. There are 3 lone pairs. We have 3 sets of paired electrons, and again, those are called lone pairs. Okay, so how many electrons are required to reach the stable noble gas configuration? Okay, I've given you some time to think of the answer, and the answer should be 1. There is only 1 electron that is needed to reach the noble gas configuration. Okay, let's do just a little bit more practice. Let's consider sodium. Now, this should be very straightforward because we have practice with other things. If we quickly think through the shells and where electrons go, we come to the conclusion that there is only one electron in the third shell. So drawing the Lewis dot could look something like that. So sodium has a very simple Lewis dot structure, and it only has one electron in the outermost shell. Okay, one thing that I forgot to talk about, so let's go ahead and step back a page, is for chlorine, chlorine had 7 valence electrons. Therefore, it only needed 1 electron to reach the noble gas configuration. Now here's sodium. Sodium only has 1 electron. So therefore, that could mean it needs 7 electrons to reach the noble gas configuration. But that sort of thing is actually not heard of. It doesn't happen in chemistry. Instead, what's going to happen for the sodium atom is it is actually going to lose its 1 electron of the third shell to reach the stable noble gas configuration. When it loses the 1 electron out of the third shell, that does mean that there are 8 electrons in the second shell. Because again, remember the electron configuration for sodium was we had 2 electrons in the first shell. We had 8 electrons in the second shell, and that left 1 electron in the third shell. Sorry, left out the 3, the third shell. And so what we're doing here is we are losing the 1 electron out of the third shell. And so sodium now has a stable noble gas configuration because the second shell is completely filled with 8 electrons. Okay, we've gone through 3 fairly straightforward Lewis dot structures. Now let's tackle an element that is a little bit more complicated, and that element is potassium. Determining the Lewis dot configuration of potassium is more complicated, and we actually need to first consider the position of potassium on the periodic table. Potassium is in the 4th row, it's right here, and so that does mean that it has electrons in its 4th shell. The row number always correlates to the shell number. So let me go ahead and go through the electron configuration. We have 2 electrons in the first shell. We have 8 electrons in the second shell. We have 8 electrons in the third shell. And then we have 1 electron in the 4th shell. And that is the configuration of potassium, which means that it has only 1 valence electron. So I'm going to add the dot to the potassium, and notice that the electron configuration, this valence electron configuration, is exactly like we determined for sodium, which is in the row directly up above. And this is in accordance with that law of periodicity. So elements that are in the same row have the same characteristics, and potassium, just like sodium, has only 1 valence electron. All of you should be saying to me right now, but wait, the third shell can hold 18 electrons. But what did I show you here in the configuration? I showed you here in the configuration that actually only 8 electrons go into the third shell. This is one of the more complicated issues in chemistry, but it fits the rule of octets. Atoms are always more stable when we have 8 electrons in a shell. And so what happens is we put 8 electrons in the third shell and then begin filling in the fourth shell. Only when there are 8 electrons in the fourth shell do we ever go back and put more electrons in the third shell. I know this is quite confusing, but if you're not sure exactly how to figure out the electron configuration of any atom that's towards the bottom of the periodic table, then what you can do is just work your way towards the top of the periodic table. Find out how many valence electrons, such like lithium has, which is pretty easy. And if you know lithium only has 1 valence electron, then therefore you know that sodium and potassium and rubidium are going to be the same. Or another example, if you determine that barium has 2 valence electrons, then you know that magnesium and calcium and the other atoms below on the periodic table also only have 2 valence electrons. Okay, we've worked through this kind of complicated issue of Lewis dot structure. Let's go ahead and move forward into information that I think becomes even more interesting. Okay, what I want to talk about is why we even care about the number of valence electrons and how many more electrons would we either need to gain or lose to make noble gas configuration. But I want to do some review before I get into the practical examples. So first, let's consider oxygen. We determined that it had 6 valence electrons. So is it more likely to gain or lose electrons to reach noble gas configuration? You're right, it is more likely to gain electrons, and specifically we are more likely to gain 2 electrons to reach the noble gas configuration. That is absolutely going to change the charge of our atom. Remember, atoms are overall neutral. But now if oxygen gains 2 electrons, that oxygen is now going to have a -2 charge. Now let's consider chlorine. Chlorine had 7 valence electrons. We are going to be more likely to gain just 1 electron to reach the noble gas configuration. So therefore the charge of the chlorine atom is going to be a -1. Sodium and potassium have 1 valence electron, and as we already talked about, it is more likely to lose 1 electron. And if an atom loses an electron, then that would mean the atom has more protons than electrons, and the charge of both sodium and potassium atoms are going to be +1. These atoms are no longer neutral and they have charges, and so these atoms are now called ions. So we would say that the oxygen ion has a 2- charge, the chlorine ion has a 1- charge, and the sodium atom has a +1 charge. Okay, so now let's move even further forward into why would we care about these charges. So now let's talk about molecules. And specifically, let's consider the combination of sodium and chlorine. The atoms sodium and the atom chlorine are neither in their stable electronic configuration. So what seems most likely to happen based on everything that we've been looking at in the past 10 minutes? And you're right, sodium is going to lose its one electron to reach this stable configuration. What's going to happen to this one electron? Well, that one electron is going to add to chlorine so that chlorine reaches its most stable configuration. This is a win-win situation. Sodium, since it has lost an electron, now becomes positively charged. Chlorine, since it gained one electron, now becomes negatively charged. And these two atoms now bond to one another. They are attracted to one another because of their opposite charge. We call this ionic bonding. These two atoms are bonded to one another because they are ions of opposite charge. Any molecule that displays this bonding pattern is generally called a salt, and you may recognize that the molecule known as sodium chloride is also the table salt that we use in the kitchen. Okay, let's move to another example. So let's consider a combination of oxygen and hydrogen atoms. Hydrogen is in the first row of the periodic table, and so to remind you, it reaches the stable configuration either by gaining one electron or losing one electron, since that first shell only holds 2 electrons. It does not strictly follow the octet rule, with octet meaning 8. Oxygen needs 2 electrons. And so you probably can already see where I'm going with this demonstration. But it's a little bit different with the sodium chloride. There is still a win-win situation that's going to happen between the oxygen atom and the 2 hydrogen atoms, but the bonding really more happens a little bit like this. So the hydrogen comes in and it combines with the oxygen on that side, and the other hydrogen comes in, combines with the oxygen on this side. And so now all of the octets are satisfied. So the hydrogen octets are satisfied because they have 2 electrons. The oxygen octet is now satisfied because it has a total of 8. But what has happened here is that the oxygen and hydrogens have participated in sharing electrons. One does not give the electron away, another atom does not take an electron, but instead all of the electrons are shared. This type of bonding is known as a covalent bond. A covalent bond is a very strong bond. Let's go back and consider sodium chloride. So sodium chloride was that ionic bond, and ionic bonds are relatively weak. So if you take table salt, you drop some table salt into water, the sodium is going to very quickly separate from the chlorine, and we actually call that dissociation. I might have spelled it right, it looks like. So that's known as dissociation, and that happens really easy when sodium chloride is dropped into water. But if now we consider water, where we have covalent bonds between the oxygen and the hydrogen atoms, in order to separate those bonds, we would actually have to apply an electric charge. Those bonds are so strong, they are very difficult to separate. So, moving forward into just a little bit of advanced information, I just want you to know that predicting if an ionic bond or covalent bond is going to form is mostly outside the scope of this class. but I want to briefly show you the information that we can use to kind of make such a prediction if we have to. Some periodic tables, like the one I have made and have shown on this slide, have information about an atom's electronegativity. The electronegativity number is in red. Electronegativity is the strength or the pull that atoms have on electrons. With chlorine, let's come over here to chlorine. We can see that its electronegativity number is relatively high. So it has a strong pull on electrons. Now let's go investigate sodium. Sodium has a low electronegativity number, and so it does not have a strong pull of electrons. Therefore, it makes sense that sodium is willing to give up an electron and chlorine is willing to take an electron. But now let's consider our last two molecules, hydrogen and oxygen, that were used to compose water, H2O. If we look at hydrogen, we see that it has a relatively high electronegativity number of 2.1, and oxygen has an even higher electronegativity number of 3.5. So neither of these atoms are likely to give up electrons. Both of them have strong pulls on electrons, so that is why it is more likely that these atoms will be involved in sharing of electrons rather than transferring of electrons. Let's go to a complicated structure. So let's consider the molecule C2H6O. This would be the chemical formula, and I've written it up here in the right-hand corner. So now what I want to have us think about is, we know about valence electrons, we know about how to draw Lewis dot structures, so how can we use this information to now draw molecules? And this is a part of chemistry that I actually find just to be a little bit fun. It's kind of like solving for a puzzle. I always begin figuring out the structure of a molecule by beginning with carbon. So I'm going to put the carbon atom here in the center. Oops, it didn't bring, oh my, now that has gone bad. You'll have to forgive my video and my inability to do editing. So I'm going to pull that carbon up to the center in a slightly different way. There we go. Okay, so there's our carbon in the center of the page. I like to begin with carbon because almost all of the chemicals that we're going to be dealing with, especially in cooking chemistry, are carbon-based. And we call carbon-based molecules as organic molecules. Organic does in a lot of ways mean natural, and natural chemicals are carbon-based, and so that is why any molecule containing at least one carbon atom is called an organic molecule. Okay, I have my carbon in the center, and now I want to begin building a molecule. I can see that none of my electrons are paired, and I know from the octet rule that I need to have all of the electrons paired. So here's my first idea. I'm going to bring in a hydrogen. So maybe I'll go ahead. Okay, so I'm going to bring in the hydrogen. I'll move the H here. I'm going to bring in its dot over here. Okay, so just a little bit on the ugly side, but I think you can see what I'm doing. So now let's go ahead and take this other hydrogen, and I'm going to bring it in over there. And so, well, that's looking pretty good. Now I have two covalent bonds that are formed. I can bring in this other hydrogen, so I'll bring it in over here. The dot got left behind, so I'll add the dot there. And okay, well now I can see I have one unpaired electron left, and so you might think, well, I'll just bring in this other hydrogen atom. But then here's the problem. if I bring in that other hydrogen atom with its one electron, that leaves no place for any of these remaining atoms to combine. So that must not be the right way to continue building the structure. And so then my idea is, okay, well, how about I bring in this other carbon? So to make things fit, I'm going to kind of twist this carbon over on its side just a little bit. Okay, so now this carbon is surrounded by 8 electrons, fulfilling the octet. And now I see I have 3 more positions to bring in other atoms. And so maybe I'll go ahead and pull this oxygen down. Okay, so now I've made a covalent bond there. Let's see, I have 2 places I need pairing, so I'm going to bring over this hydrogen, maybe do a little bit of twisting around to make it work. Okay, there's that. Again, this is a lot like solving for a puzzle. I see that I have an unpaired electron there. So my idea is, well, I'll probably need to be bringing in another hydrogen there. Okay, so I'll bring in and fit it there. And so I can see now that this second carbon has its octet completely filled. And now when I consider the oxygen, I just have 1 unpaired electron, and it makes complete sense that that must be where this other hydrogen goes. Okay, so again, it's like a puzzle. I'm fitting all of the pieces together. Okay, so there it is. I've solved for my puzzle. So this is one of the ways that 2 carbons, 6 hydrogens, and an oxygen can combine together to form a molecule. So I have CH3, and then bonded next I have a CH2 unit, and then bonded next I have an OH. And actually this is the molecule ethanol, which is the one edible alcohol that's found in our alcoholic drinks. Okay, so I consider that a lot of fun. You'll have some practice with this exercise later, but I want to go ahead and move on to just a couple of other very small ideas that I can present in just a couple of more minutes. So the next idea I want to present is that if we as chemists were to draw molecules all the time using dots, that would get very tedious, and so therefore we don't. The other kind of drawing style is shown like this. And actually this is much easier to see than having all of those dots in the way. This is known simply as a Lewis structure. The structure right here is called a Lewis dot structure because we represent all of the electrons as dots. And this is just a Lewis structure. Wherever we had electrons paired, we draw a line, and so therefore we can say that every line represents 1 covalent bond. What some people will do in a Lewis structure is also go ahead and add the lone pair electrons as dots. So this is sometimes done, this is sometimes not done. You'll even see that sometimes I'll draw in the dots and sometimes I won't. There's no one specific rule for Lewis structures. This is definitely an easier way to draw a chemical structure, but the one easier way looks like this. And this is known as a line angle drawing. Line angle drawings can be very difficult to read, but I hope within a week you'll be able to read these kind of drawings very easily. So first, you notice that there were carbon and hydrogens drawn in the previous drawing, but they're missing now. What we say is that these carbon and hydrogens are implicit in the drawing. They are implied. At every end of a line and at every angle, we have a carbon atom and the appropriate number of hydrogen atoms. Now notice though the oxygen and hydrogen are drawn in, so any non-carbon atom has to be drawn in, and it is said to be explicit in the drawing. It is explained in the drawing. And so we have the oxygen atom, and then since it's an oxygen atom bonded to a hydrogen, usually the hydrogen atom is also drawn in. And this is known as a line angle drawing. Okay, so that's the end of this video. We have covered a lot of material. Most of this material is going to be covered again in the quiz you're going to take. I strongly recommend whenever you come to a certain question on the quiz that you can't quite answer, that you come back to this video and re-watch certain sections.